Hello and welcome to this video for Doppler effect for level 3 physics and for the standard 3.3 for waves, so it's wave systems. So at the end of the presentation, I also have some scholarship level questions for those who are taking the scholarship exam this year. It will be some good practice questions at the end, so stay tuned. Alright, so we want to get into what is the Doppler effect. So the Doppler effect is a apparent change in frequency when a source is moving relative to an observer. Relative means that the source could either be moving or the observer or both at the same time. Okay. So we can actually observe the Doppler effect in real life. So if we imagine that you're on a sidewalk and you hear an ambulance, the siren is on, and you hear the ambulance approaching, you actually hear a higher frequency as it is approaching you. And as soon as it passes you, you'll hear that frequency drop. Like all of a sudden, that frequency is going to drop, and as the ambulance moves away, you're going to hear a lower frequency than when it was approaching you. So that's actually the Doppler effect. So we observe this in real life when the ambulance passes us, so just as I said, so we don't hear the same sound throughout. We hear a high-pitched sound as the ambulance is moving towards us, and a lower frequency when it's moving away from us. In NCA Level 3 physics, we only consider sound waves. But in real life, the Doppler effect can be observed in many more types of waves, such as light waves, radio waves, etc. So one example of Doppler effect in light waves may be if a scientist is observing a planet, if the planet is showing a redshift, a slightly more red color, we know red has a larger wavelength, which means that the observed frequency is actually lower, which actually means that the planet is actually moving away from Earth. Likewise, if the planet is slightly more blue shifted, then it'll mean the planet is actually heading towards the Earth. So that would be an example of the Doppler effect in light waves. And so why do we observe different frequencies if a source is moving relative to an observer? So when a source is moving, we know that the actual speed of the waves is the same because speed of waves is the property of the medium. So we know we covered in level 2 physics that refraction occurs in the bending of light when when waves pass from one medium to another medium. So that's when the speed changes, and the amount the speed changes is depending on the refractive index of the other medium. However, we know that if the waves stay in the same medium, then there's actually going to be no change to the speed of the wave. So same medium, same speed. The actual frequency and the wavelength of the wave is the same because we know that the speed is the same, the frequency is the same, so therefore v equals to f lambda, wavelength has to be the same as well. So however, we know that because of the relative motion of the source to the observer, the distance moved by the source is causing waves to be concentrated in a smaller distance or a larger distance, depending on whether the source is moving towards or away from the observer. Right, so when we see waves in a smaller distance, for example, that would be when the source is moving towards the observer. So when the source is moving towards the observer, because it moves a certain distance and then emits another wavefront, the distance between the two subsequent wavefronts will actually be lower, which means that the observer there will be observing a lower wavelength. And because v equals to f lambda, we know that lambda is inversely proportional to frequency because we know the speed of the wave stays the same. So that means that our observed frequency would increase in that case. So when the source is moving towards the observer, the movement of the source towards the observer causes the same amount of wavefront. So because we know frequency is the same, and frequency is the amount of waves produced per second, we know that stays the same. So the same amount of wavefronts are concentrated in a smaller distance. If the source is moving towards the observer, it's in a smaller distance, therefore we observe a higher frequency. If the source is moving away from the observer, we can see that the same amount of wavefronts will now be concentrated in a larger distance, which means that we'll be observing a larger wavelength, which means that the observed frequency will decrease. Alright, so likewise, when the source is moving away, the movement of the source away from the observer causes the same number of waves to be concentrated in a larger distance, meaning the observed wavelength is higher and the observed frequency is lower. So that's the theory behind the Doppler effect. So if we look at deriving a formula for the observed frequency, so we see when a source is moving towards an observer. So when t equals to 0, so that's at the start, we have a moving source, and the speed of the moving source will denote it as vs, and that's going to be emitting a wave that is moving at a velocity of vw. Alright, so after some t seconds, we don't know, t could be anything, could be 10 seconds, could be 20 seconds. So just after t amount of seconds, we know that the number of wavelengths produced by, the number of wavefronts produced by the source will be equal to the frequency times of the time of t. That's because frequency is the number of waves produced per second. So if we multiply by t, we'll get the total amount of wavefronts produced in that t amount of seconds. Alright, so we know that in t seconds, the wave would have traveled vw times of t, because d equals to v times of t. Speed is constant, so d equals to speed of the wave times time. Likewise, the speed of the source, okay, so distance traveled by the source will be equal to the speed of the source times of the time. So we notice that the source has moved some distance, and also the waves have moved some distance. And now we notice that the same number of wavelengths, so that's the total number of wavefronts, frequency times time, is now concentrated in a smaller distance because the source is moving towards the observer. So in this case, our big distance here is our total distance traveled by a wave, and our source would have also traveled some distance, and then the distance in between would be the distance traveled by the wave minus the distance traveled by the source, and this is the distance that the same number of wavefronts are now concentrated in. So therefore, our actual observed wavelength will be lower, and hence our observed frequency will increase. Alright, so looking at the formula now, so as we've seen from our previous slide, we have f times t wavefronts in the distance traveled by the wave minus the distance traveled by the source. The wavelength of each wave will be the total distance divided by the number of wavefronts in that distance. So the wavelength, so I should have said the observed wavelength, so the observed wavelength of each wave would be the total distance, so the total distance divided by the number of wavefronts. So if there's 5 wavefronts and 10 meters, then the wavelength would be 2 meters, because there's 5 wavefronts and 10 meters. So similar idea here. So we know our observed wavelength, so our lambda dash. So when I write a dash, that just means that's the observed frequency, or that's the observed wavelength. So similarly, if I wrote f dash, that would mean that would be the observed frequency. So we know our observed wavelength is equal to t. I factored out t, so t bracket the speed of the wave minus speed of the source, all divided by the number of wavefronts, which is f times of t. So you know that t is a common factor, we can just cancel that one out, so the time actually doesn't matter. And so wavelength dash, that's observed wavelength, frequency is the actual frequency, and we know that time here cancels out. So right, so we know our speed stays the same because the speed of the waves is the property of the medium. So if it's in the same medium, it's going to be moving at the same speed. So therefore, our v is equal to our observed frequency times our observed wavelength, and v also equals to our actual frequency times our actual wavelength, because v is the same. Alright. So we know speed is the same medium, and that speed is just equal to the speed of the wave as we defined in our previous slide. Right, so now we can rearrange for observed frequency, because now we know that speed of the wave equals to observed frequency times of Vw minus Vs over the actual frequency. And if we rearrange for the observed frequency, we'll get the observed frequency equals to the actual frequency multiplied by the speed of the wave divided by the speed of the wave minus the speed of the source. So that will be our formula for the Doppler effect for the source moving towards the observer. Alright, so what about if we're moving away from the observer? What if we're going the other side? So when the source was moving away from the observer, the distance that the f times t number of wavefronts is in will be Vs plus Vw, because in this case, the source will be moving away from the observer. So yeah, opposite direction to when the source is moving towards the observer, so it will become Vs plus the speed of the wave. That will be the distance. Hence, the formula is f dash, so observed frequency equals to the actual frequency times by the speed of the wave divided by the speed of the wave plus the speed of the source. So in this case, we can see that everything in both formulas is the same except for the plus and the minus sign between the Vw and Vs. So therefore, we can generalize our formula. So the formula on the formula sheet will be given as the observed frequency equals to the actual frequency multiplied by the speed of the wave divided by the speed of the wave plus or minus Vs. So in this case, when you're doing your exam, you have to understand which one you have to use for which scenario. So we use the plus sign, so that's when the source is moving away from the observer, and that's resulting in the observed frequency to be lower than the actual frequency. The subtraction sign is used when the source is moving towards the observer, so in this case, the observed frequency is actually higher than the actual frequency. So one important thing to remember is that the Vs, so that's the speed of the source, is representing the relative velocity of the source to the observer. So Vs doesn't necessarily mean the velocity of the source. It's only the velocity of the source relative to the observer. So we always have to take a relativity to the observer. Alright, and remember that this formula that we just derived here is only if the the observer is stationary and the source is moving away or towards the observer. So only when the source is moving and stationary observer. It doesn't work for any of the other cases. For example, if the source and the observer were both moving, or if the observer was moving and the source is stationary, this formula wouldn't work, okay? However, in level 3 physics, we only do the stationary we only do the stationary observer and the moving source. So this is the only formula you need to know. Right, here's a practice question. So Kevin was sitting down on a bench when he noticed a police car approaching him at 100 kilometers per hour. Its siren emits a natural frequency of 230 hertz. So we're going to be using the speed of sound in air as 340 meters per second. So in the exam, they might make you use it as 340 meters per second or 330 meters per second. I don't know. They sometimes change it around, okay? So question A, calculate the frequency that Kevin hears. So calculate the observed frequency. Alright, so just pause the video now and try this question for yourself, and when you're done, just continue watching. Alright, so for this question, we notice that the police car is approaching him, which means that the observed frequency will be higher, and therefore we're going to be using the minus sign in our formula. So we know our f dash equals to our actual frequency and times our speed of the wave divided by speed of the wave minus speed of the source. If we plug our numbers in, which is a plug and chug, so our observed frequency would be equal to everything inside. But we know that kilometers per hour, if we divide kilometers per hour by 3.6, we'll get meters per second. So this is why I divided by 3.6, because when we're doing Doppler effect, everything has to be in meters per second, just to remember that. Right, so if we substitute into our formula, we'll get that our observed frequency is 250.46 hertz, and if we round that to 2SF, we'll get 250 hertz. So that's just a basic achieved question there. Alright, question B, this is a very common NCA question. So explain why the frequency heard by Kevin was higher than the actual frequency. So the observed frequency is higher than the actual frequency because of the relative motion of the police car towards Kevin. When the police car produces a sine wave, its motion means that the next subsequent wave is produced closer to the previous wave, the wave that it first produced. So the second wave it produced, because it's already moved a little bit, the second wave it produces will be closer to the first wave it produced rather than if it was stationary. If it was stationary, then it would be lambda apart, but in this case the source is moved some distance, which means that the subsequent wave is produced is closer to the first wave it produced, which means that the wavelength between these two waves is smaller, therefore the observed frequency is higher. So we know frequency is constant, the same number of waves is concentrated in the shorter distance, meaning that the observed wavelength must be smaller. Because velocity equals to the wavelength times frequency, the observed wavelength is smaller, therefore the observed frequency must be higher. So that would be your basic explanation there. This is usually a merit level question for NCEA. Very common question that will either make you explain why the frequency was higher or why the frequency was lower, depending on which way the source is moving. So very, very common NCEA question here. So question C, when Kevin told the police officer that the frequency he heard was 250 hertz when the car was approaching and the police officer was confused, state the frequency the officer heard and explain why he didn't hear a frequency of 250 hertz. Alright, so for this question, the police officer will always just be hearing a constant frequency of 230 hertz, not 250 hertz. So 230 hertz, it will be the actual frequency of the siren. So this is because the police car and the police officer is acting as if it's a system, and the police officer is actually traveling at the same velocity as the car. So they're both going at a certain direction at the same speed, which means that their velocity is the same, and therefore there's actually no relative velocity between them. So therefore, in other words, the officer is stationary with respect to the police car. And because the police officer is stationary with respect to the police car, then we can just consider it as no Doppler effect. So therefore, Doppler effect is not a factor in this case. So Doppler effect can only be observed if a source is moving relative to an observer. Since there is no relative motion of the source to the observer, then it will be the same as just the stationary observer and the stationary source, which means that the policeman will hear the frequency of the siren, which is 230 hertz. So that would be another common NCA question. So asking you to explain why a person driving a car hears the same frequency. So another very common merit level question for NCA. Right, so question D. The police officer drives off in his car, siren still sounding at 230 Hz. He travels again at 100 km per hour, but is now driving away from Kevin, who is still sitting stationary at his bench. Kevin now hears a lower frequency and calculate this frequency. So just pause the video now and then try these questions for yourself. Right, so for this question, instead of using, because now the source is moving away from the observer, we're going to be using the plus sign with the formula. So we're going to be f dash equals to f times of VW over VW times, plus of Vs. So we just plug our numbers in again, so we should get that our observed frequency this time is 212.63 Hz, which if we round that down to 2SF, that's 210 Hz. Alright, so Kevin notices that the lower frequency he heard when the police car was moving away was closer to the actual frequency than the higher frequency he heard as the police car was approaching. So this question asks you to explain why the Doppler effect is not symmetrical. Alright, so we say that the Doppler effect is not symmetrical. So when I say not symmetrical, that means when the source is approaching, I'm going to hear a higher frequency. And this high frequency is x more than the actual frequency. When the source is moving away, then the frequency will be lower, but that means when I say it's not symmetrical, that means the observed frequency when the source is moving away is not x lower than the actual frequency. So that's what I mean by not symmetrical. So this is because that when the source is approaching, if the source's speed is equal to or greater than the actual speed, if the source speed is equal to or greater than the actual speed, then the observer would actually not hear anything. And that's because in 1 second, the source is actually moving more distance than the waves, which means that there's actually a lag effect with the waves, which means that if Kevin was an observer, he wouldn't hear anything if the car was moving faster than the waves. So as soon as the police car passes him, he would hear this big boom sound, which some people might call a sonic boom, and that would be due to the lag effect. However, if the source is moving away from Kevin, so if the police car was moving away from Kevin, no matter what the speed of that car is, even if it's a lot faster than the speed of the sound, Kevin will still hear a frequency. Even though that frequency is very low, he will still hear a frequency no matter how fast that car is moving. And that's because the wavelengths will always be able to reach Kevin from the back. So he'll always be able to hear a frequency, and that's why the Doppler effect isn't asymmetrical. Right, so here's some excellent calculation questions. So on another occasion, Kevin hears a frequency of 500 Hz as an ambulance was approaching and 420 Hz as the ambulance was heading away. Assuming the ambulance maintains a constant speed, calculate the speed of the ambulance. So this will be a very standard excellence level calculation in the exam. Maybe the excellence questions might be a bit more easier than this, but just for challenge yourself to with this question. So give yourself some time. It might take a while, so just take your time and try to find the answer to this question, and then keep watching for the answer. Right, for this answer, at first you might just say, oh, we're only given two frequencies, so how can we possibly be able to find the speed of the source? Well, in this case, yes, we only have two frequencies. However, we know that because it's the same source, that means the actual frequency in both cases are the same, and that means these two variables are really all that we need in order to find the speed of the source. So looking at our two formulas, we have 500 equals to our actual frequency times our 340 divided by 340 minus the speed of the source. It's minus Vs in the first formula because it's moving towards Kevin. The frequency observed is higher. In the second equation, we have 420 equals to the actual frequency times our 340 divided by 340 plus Vs. It's plus Vs in this case because the ambulance was heading away, so the observed frequency is lower. So in this case, some people might choose to rearrange for f and then make the two equations equal to each other, but usually that way takes a lot longer, and you might have a higher chance of making a mistake. So what I like to do here is let's just say we just divide formula 1 by formula 2. So that's the case of simultaneous equations. So you can multiply by any equations and they'll still be true. So I'll say the equation 1 divided by equation 2. So in this case we'll have 500 divided by 420. That equals to f over f. That's just 1. So we can just get rid of the f. and that's equal to 340 divided by 340 minus Vs divided by 340 divided by 340 plus Vs. And if we rearrange that formula, we'll get 500 divided by 420 equals to 340 plus Vs over 340 minus Vs. So now realize we only have the Vs left, and now we can use our algebraic manipulation in order to solve for Vs. Alright, so in this case, just following basic algebra, so we cross multiply, we expand the brackets, and we move Vs to one side, and we move the constant to the other side, and we divide through 920 on both sides, and we'll get the Vs equals to 29.57 meters per second, which is equal to 3.0 plus times 10 to the power of 1 meters per second, and that's rounded to 2SF. Alright, so here's another question. So a train is traveling at 28 meters per second, and it begins to decelerate upon approaching Artarmon station. It's a constant deceleration. At the moment the head of the train reaches the edge of the station, Kevin hears a frequency of 78 Hz as he is standing on the opposite edge of the station. So the train comes from one side of the station, Kevin is all the way on the other side of the station. When he hears the train, when the head of the train has reached Kevin 4 seconds later, so 4 seconds after the train reaches one edge of the station, it reaches Kevin's edge of the station, and in that case, Kevin heard a frequency of 72 Hz. So calculate the length of the station, assuming the train was still approaching Kevin after 4 seconds. So once again, a very challenging question, but just give yourself some time and try and solve this question by yourself, and watch. And after you found the answer, you can keep watching for the answer. Alright, so for this question, we know that because the train is decelerating and the train is still approaching Kevin, so when the source is approaching an observer, we're going to hear a higher frequency. And the magnitude of this increase of frequency is dependent on how fast the source is moving. So because the speed of the source is actually decreasing over time, that means the observed frequency of Kevin will also decrease over time, which makes sense because the second frequency Kevin heard was lower than the first frequency he heard. Alright, so we know acceleration is constant, as we mentioned in the question. Well, technically I should say deceleration is constant. So therefore our Vf equals to our Vi plus At. We know our Vi is 28, but for now I'll just write it for Vs. Okay, I'll write 28 as Vs for now. So that will be equal to Vs minus 4 times the A. A we do not know. Alright, so now we're going to write down both our equations we know. So we know 78 equals to our actual frequency times our 340 divided by 340 minus our speed of the source. And then 72 equals to our frequency times by 340 divided by 340 minus bracket. Remember the bracket because we have Vs plus, okay, so I actually made a slight mistake here. So Vs, Vs meant to be Vs plus 4a because you don't know well, technically we know that the acceleration is negative. However, because we're just going to put a plus sign in front of it now, and we'll work out that the acceleration is negative. So 340 minus our speed of the source plus of 4a. So those are our two equations again, and like the previous question, we can actually divide through both equations. So equation 1 divided by equation 2, so we'll get that 78 over 72 equals 2. Equation 1 divided by equation 2, so you should get that 78 over 72 equals to 340 minus 4a minus Vs over 340 minus Vs. However, now we know that Vs is 28 meters per second because that's when it starts to decelerate. That's our initial speed of the source. So plugging our Vs for 28, we can solve for our acceleration. So in this case, when we plug our Vs as 28, we can once again use our algebraic manipulation. We can expand the brackets. So first I cross multiplied, and then I expanded the brackets, and then I rearranged so that a is on one side, and then the constants on one side, and then I divide through both the constants, so then I'll get A. So A should come out to be negative 6.5 meters per second squared, meters per second to the power of negative 2, okay? So we have our acceleration now. So now we can use our kinematic equations in order to find out how far the train traveled in this distance. So we know the acceleration is constant, so therefore we can use kinematic equations. If the acceleration isn't constant, we cannot use kinematic equations. So in this case, we'll be using d equals to initial velocity times the time plus half at squared. We know the initial velocity is 28. We know the time taken is 4 seconds. We know the deceleration is 6.5, and then our time is 4 again. So therefore, we plug these numbers in, and we should get that our distance is 60 meters. So therefore, the station is 60 meters long. That's your final statement. Alright, so here's another example. So now we have a graph here. So this graph actually shows the frequency over time that Kevin here. So this is frequency on the y-axis and time on the x-axis. So 1 square is actually equal to 10 seconds here. So 1 squared equals to 10 seconds. Alright, so the train starts at rest. Okay, so question A, explain what is happening in the first 10 seconds and how you know this. Calculate the average acceleration. Alright, so in this case, we know that our frequency increases, so it starts at 850 and it increases. We know that the train starts at rest, it starts stationary. So because it starts stationary, we know that a stationary source and a stationary observer, we know that we will be hearing the actual frequency. So therefore, looking at our graph, we know automatically that our actual frequency is 850 hertz. We know that our the final frequency we hear is 950 hertz, and that's after some speed. We don't know how much speed, but that's after some speed is gained by the train. If we find out what speed is gained by this train, and then we can use our kinematic equations to find our average acceleration. Alright, so the first 10 seconds the train is accelerating at Kevin, though not at a constant acceleration. So we know that's because the frequency that Kevin hears increases exponentially, and the rate of increase, I should say rate of increase. So the rate of increase decreases at around 6 to 10 seconds. So we can see that as when the train first starts, we see a rapid rise in the frequency heard, but after some time that rise starts to slow down, and then it slows down after 10 seconds. After 10 seconds, we hear a constant frequency of 950 hertz. We know that it's accelerating because we know that when a source is moving towards an observer, the observed frequency will be higher, and the amount of the frequency increase is dependent on how fast the source is moving. So the faster the source is moving, the higher the observed frequency. So in this case, our observed frequency increases, and we know that the train is moving towards Kevin. So in this case, we know that the speed of the train must be increasing, and hence it must be accelerating, because acceleration is the rate of change of velocity of the train. And so the relative velocity of the train to Kevin must be increasing, as Kevin is hearing a high frequency over time. Alright, so finding the speed is then find the speed the train is traveling at when Kevin hits a 950 hertz sound, and then calculate the average acceleration this time. So 950, sorry about the cursor, is might be blocking your view, apologies. So 950 equals to 850 multiplied by 340 over 340 minus Vs. If we cross multiply and then solve for Vs, we'll get 35.79 meters per second. And if we use Vf equals to Vi plus At, we'll get that our acceleration is 3.6 meters per second. And that's we can use our kinematic equations in this case, because we're trying to find the average acceleration. Okay, because we cannot find the precise acceleration because. We cannot find the precise acceleration because we know that the acceleration isn't constant, because the frequency increases very quickly and then it starts increasing more slowly. So therefore, we know the acceleration at the start of the trip is a lot more than the acceleration after about 5 seconds. So after about 5 seconds, the acceleration starts to decrease, and after 10 seconds, there is no longer any acceleration. So we know the average acceleration is 3.6 meters per second. Right, so when does the train pass Kevin, and how do you know this? Right, so about after 30 seconds, the train passes Kevin. We know this because we experienced a sudden drop in frequency. That's a Doppler drop, and that's heard by Kevin. Graphically, this is represented by the vertical line down. Okay, so how about in real life? We know that Kevin hears the actual frequency 850 hertz, and this is because after 30 seconds, the train is in line with Kevin, and therefore at that exact moment, the train isn't moving away, and it isn't moving away from Kevin, because there's no relative, even though the train is still moving at that second, there is no relative velocity at that time. So that's what's important about the Doppler effect, because you have to know that Vs isn't the velocity of the train. Because technically you can say that the train is still moving. However, there is no relative velocity there is no velocity relative to Kevin, and therefore because there is no velocity relative to Kevin, therefore the frequency heard will be same as the actual frequency, which is 850 hertz. And graphically, we see this as a straight line down, because that's when we go from hearing the high frequency when the source is approaching, and then we hear a big drop in the frequency, and that's when a train passes us, and then we'll hear a lower frequency when the train goes away. Question C. Explain what is happening from 30 to 75 seconds. Alright, the train must be decelerating after 30 seconds. We know this because the train has already passed Kevin, meaning that the faster the train, the lower the observed frequency. However, we see in the graph that the frequency is increasing. Alright, so there might be you might think there's a little bit of a contradiction here, because when the train passes Kevin, we should be seeing a big drop in the frequency. In the graph, we do see a drop in the frequency. However, after the drop, we see an increase in frequency again. Because we know that the train is now moving away from Kevin, the amount of the frequency is less than the actual frequency is determined by the speed of the train. So the faster the train moving away from Kevin, the lower the frequency will be. So because the frequency starts to increase, that means the speed that the train is moving must be decreasing over time, because the frequency I'm hearing, the observed frequency, is increasing. So therefore, we know that the speed of the train is decreasing, that means it must be decelerating. So this means the relative velocity of the train traveling away from Kevin must be decreasing, hence the train is slowing down. We see that the deceleration is not constant as the rising gradient, so we know that the curve gradient is larger at the start, which means that the deceleration was more rapid at the start than at the end. Because at the end we see a lower gradient, which means that the rate of decrease of the speed is starting to slow down, and that means that just means that the rate of increase of our observed frequency will also slow down. Alright. So calculations. Knowing this information, Kevin wishes to know the distance between Artarmon Station and Chatswood Station. Assuming the train leaves Artarmon at t equals to 10 seconds and arrives at Chatswood after it has first stopped, calculate the distance between the stations. For this calculation, you may assume the acceleration and deceleration is constant. Okay, so there's actually a bit of a problem with this question. The main problem is that the acceleration and deceleration is not constant, because we saw that the acceleration and the deceleration, it was represented by the curve, because the frequency did not increase at a linear rate. The frequency was increasing faster at the start when the train was approaching. When the train was approaching, the frequency was increasing very quickly, and then it started to flatten out. That means the acceleration isn't constant. Same with after the train has passed Kevin, the frequency rises very quickly, and then it starts to flatten out again much slower. That means that the deceleration isn't constant either. So technically that means we cannot use our kinematic equations, because our kinematic equations can only be used if the acceleration is constant throughout. If we really wanted to find the true distance, in this case, we have to find the equations of the curve. We have to bring in calculus, and because this is a physics course, I don't want to bring in calculus. So therefore, I'm just going to allow you to assume that the acceleration and deceleration is constant. Right. So give a go at this question and keep watching after you have after you wish to see the answer. Alright, so in this case, we have to do this question one part by one part. So part 1 would be the acceleration, part 2 would be a constant speed, part 3 would be the deceleration. So you have to do this in 3 parts. So looking at part 1 from 0 to 10 seconds, we know that the distance equals to v, the initial velocity plus the final velocity divided by 2 times the total time. We know that the final velocity is 35.79, the initial velocity is 0, and the time taken is 10 seconds. Therefore, our distance is 178.95 meters. So that's the distance traveled in our first segment. And the 35.79 was figured out in the previous question. Remember that when we were calculating the average acceleration, we had to work out the final velocity. So 35.79 was the final velocity there. So our distance traveled in this case is 178.95 meters. Right, so from 10 to 30 seconds, that's the flat line. That's a tiny bit of flat line after 10 seconds. Because the frequency is the same that's heard by Kevin, that means because the train is still approaching Kevin hears a higher frequency than the actual frequency. However, this observed frequency isn't increasing or decreasing, and that means because the increase of the frequency is determined by the speed of the source. Because they're staying the same, that means the speed of the source also stays the same. So that means we calculated 35.79 meters per second in our previous question. That was the final velocity after 10 seconds, which means that after 10 seconds, it will continue to go at 35.79 meters per second for another 20 seconds. So in this case, constant velocity, we can just use our kinematic equations again. So in this case, we can use d equals to vt because our velocity is constant. We can only use this formula because our velocity is constant. If it's not constant, we cannot use this equation. We have to use the kinematic equation. So d equals to 35.79 times 20. So our distance traveled is 715.8 meters. That's our segment number 2. Segment number 3, that's from 30 to 75 seconds. So in this case, we know that after 75 seconds, we see a flat line, and that flat line occurs at 850 hertz. Because that flat line is at 850 hertz, and we know 850 hertz is the actual frequency of the train, that means that there has to be no Doppler effect. We know Kevin is stationary, and the Doppler effect doesn't happen if there's no relative movement of the source away from the observer. Because Kevin is stationary, that means the train also has to be stationary. And if we know that this train is stationary, that means we know that the velocity is 0 meters per second. So therefore, our final velocity is 0 meters per second. Our initial velocity is 35.79 meters per second. Our time would be the time in between, which is 45 seconds. And we can use that to find our d value. So we know that the final velocity of the train is 0 because Kevin hears the same frequency as the actual frequency. Hence, the source must not be moving as Kevin isn't moving. So once again, we use d equals to vi plus vf over 2 times of time, and we get that our distance is 805.275 meters. Alright, so now we want to find the total distance traveled in order to find the distance between our Talman Station and Chatsworth. So we add all the distances traveled together, and we should be getting that our total distance traveled is 1,700 meters. And that will be your final answer for this question. Right, so that brings us to our end of NCA Level 3 Physics. For the scholarship part, I might cover it in a separate video. And this is just for the Level 3. So for Level 3, if you were able to do those last 3 questions, if you understand what was going on in those X and level calculations and the explanations, then you'll be okay for the exam. Alright, so thank you for watching this video. I hope to see you all in the next one. Thank you. Bye.